All right, we have a recording going. So hopefully this will record and we can put it online for future reference and for those who are not here today. But I have three functions on this page, and I would like you to use the definition of the derivative, which you all know is that limit equation. Use the definition of the derivative to find each of these three derivatives, please. So I'll give you a few minutes to work on that, and I will pause the video. There's my work for number one. You can compare it with yours. There's my answer for number two. Looked like lots of people are getting the same thing as me. A little bit more time, and then I'll go over number three. Anybody have any questions with numbers one or two? One or two were good. All right. For number three, here's my work. So I get negative 1 over t squared. Questions on this one? Okay, some of you are still writing some of this down. I'm going to go on to fill in this table at the bottom of the page here with derivatives that we found so far. So, question number one, the derivative of x squared we found is 2x. For number two, the derivative of x cubed we found was 3x squared. And then finally, for number three, I'm going to rewrite this as negative t to the negative 2. So this would be negative x to the negative 2. If we were to look at the pattern here and follow it, and some of you already know the power rule, so I guess you could speak up if you like. What would the pattern tell us we would get for x to the fourth? Derivative would be what? Daniel? 4x. Yeah, 4x cubed. And x to the fifth would be 5x to the exponent 4. Thank you. And derivative of x to the negative 2 would be negative 2x to negative 3. So we could have done all of these using the definition of the derivative, but I thought just doing 3 of them would be enough to see the pattern. In science, this is how things are done. So in science, we look for a pattern, and then if it's repeatable, then eventually we create a law. In math, that's not good enough. In math, we prove things. But before we prove it, let me just fill it in here on the next page for you. If I have a function, f of x, which is equal to x to the exponent n, where n could be any real number. Gentlemen, you're with me? Thank you. Then the derivative, we bring down the exponent, keep the base, subtract 1 from the exponent. So here I've written it with the two notations, with the f prime notation and with the derivative with respect to x notation. So this is a little bit different. When I write this d over dx is saying I'm going to find the derivative with respect to x of the function that follows. So it's saying the derivative with respect to x of x to the exponent n. Okay, and the derivative n to the exponent, or I should say n times x to the exponent n minus 1. We want to prove it. So I didn't leave space for this in your notes, and I won't ask you to repeat it, but doing math in university, proofs are all over the place. So let's see what we can figure out here. We want to find the derivative of this function. And so when we're going to prove something, we go back to definitions. So we're going to say f prime of x will equal the limit as h approaches 0 of my function. Well, let's just write out the definition first. F of x plus h minus f of x all over h. Step one, we're good. Now we need to apply it to this specific function. Although it is kind of a generic function because we don't know what the number in the exponent is, it could be any real number. So I'll have x plus h to the exponent n minus x to the exponent n all over h. Good? Now, how can we simplify this? From all the questions you've done, you know that we want to expand the numerator, collect the like terms, get this x to the exponent n to cancel out, so all my terms have h's, so I have a common factor of h. So how do we expand this? So how can I expand this x plus h to the exponent n? Math 30-1, very last lesson, binomial theorem. Yeah. So this whole thing to the exponent n, binomial theorem tells me I will start with n choose 0, x to the exponent n, plus n choose 1, x to the exponent n minus 1. Oh, wait, I'm missing something. I need h to the exponent 1. Next term will be what? N choose 2, x to the exponent n minus 2, h to the exponent 2. Now, how many terms am I going to have? N plus 1. But what is n? I don't know. So we're just going to summarize a bunch of it and then write down, I'm going to need more space here. I was just going to write the last term. Let's see if we can fit in 2 terms. So I'll shift this over a bit. So my second last term, what's that going to look like? N choose. What's my last term going to be? Maybe we'll do that first. N choose what? N. And x would be to the exponent 0, so I'd only have h to the exponent n. So my second last term will be n choose n minus 1, x to the exponent 1, h to the n minus 1. So that's the expansion from the binomial theorem for this x plus h all to the exponent n. And then still in my numerator, I have a minus x to the n. And then all of this is over top of h. So far, so good? Okay. What is 5 choose 0? 1. What is 20 choose 0? 1. What is n choose 0? 1. So this is a 1. So what I have, as h approaches 0, of x to the n plus all this other stuff. But before I do all the rest of it, what will n choose 1 equal? N, yeah. So that's going to be n x to the n minus 1 times h. And then my next term, n choose 2, which I don't know because I don't know the n value. X to the n minus 2, h squared, plus all the stuff. And then I'll just do the last term. Oh, what's n choose n equal to? Also 1. So I just have h to the n as my last term, minus x to the n all over h. Good? Everything making logical sense, which is math. What happens to x to the exponent n? Cancels out. So this term and that term cancels out. All the other terms have an h in them. So I could factor out a common factor. Maybe I will do that just to make it obvious. That's typically what we've done. So I'm going to factor out an h, and then I'll have nx to the n minus 1 plus nc2 x to the n minus 2, now h to the 1, plus all the in-between terms. And then I factored an h out from there, so I have a plus h to the n minus 1. All over h. Good? What's going to happen? My h's cancel out. What happens to all my other h's? Goes to 0. What am I left with? nx to the n minus 1. And we've proven that the derivative of x to any exponent will always be that exponent x to 1 less than what the exponent was before. So math is beautiful because partly we can prove things like this. Not everything can be proven like that, in math even, but in math that's often our goal. So there we go. Power rule. Question. You don't have to know the proof for a test, but it's great if you can understand it, because the more you understand proofs, the easier math in university is going to be, because proofs will show up so much. Okay, so using that rule, what would the derivative, well, let's start with this number 5. What's the derivative of 2x? Well, we think of this as having an exponent of 1. So my y prime, bring down the exponent, 1, times this 2 that I have. And then for the x, I subtract 1 from the exponent, x to the 0. So this derivative is equal to 2. And if you stop and think about it, Muhaymin, who's listening to me and not Sharia, and this is getting recorded for the world to listen to. There we go, yep. What's the slope of this line? 2, because we know y equals mx plus b. Well, yeah, the slope is the derivative, and it's a constant slope. For number 4, what's the slope of this line? 0. Yeah, so what we would do is we'd think this is 2x to the exponent 0. We bring down that 0, multiply it to the 2x, and subtract 1, and 0 times anything, still 0. So slope of the horizontal line is 0, so the derivative of a constant is always 0. Number 6, this one we already did on the previous page. We found derivative is 2x. So let's think about if we were going to sketch the graph of the derivative. So don't think of the 2x, but just think of this function. Here, my slope is 0, so my y-intercept for the derivative is 0. As we go from left to right, Ryan, you're with me? Okay, I have a negative slope, goes to 0, goes positive, that's all that's happening. Negative y value goes to 0, goes positive. Not a perfect graph, but it's linear, and if I wanted to know exactly what the graph is, it's y equals 2x. Yes? Oh yeah, so the prime symbol, just like up here in this function f prime of x, that just means we're looking at the derivative. So sometimes we'll just write it as y prime if we don't have f of x, or I could have written each of these as dy dx equals 2. So the derivative of y with respect to x. Okay? Now, way back on page 13, there were all these rules about limits that if you were doing something like the limit as x approached a, whatever the limit is, of f of x plus g of x, this would be the same as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And there were a whole bunch of rules on that page that we could make use of. So what this is telling me is if I have something like x squared plus 4x to the fifth, I can take the derivative of each part separately and then just add them together later. So that's what we'll do here. We'll just do the derivative of each part separately. So f prime of x, what's the derivative of x to the fourth? 4x cubed. Derivative of x cubed, 3x squared. Derivative of x squared, 2x. Would you rather do this or use the definition of the derivative to find the derivative of x to the fourth plus x cubed minus x squared? Probably this. And that's the joy of this chapter. We find shortcuts like this for finding derivatives. And this is the foundational one, and we call it the power rule. Because we have a power, base is x, the exponent could be any real number. All right. Why don't you try 8 and 9? But first, question.
Would you want to simplify what your equation, like your f prime, for example?
There are times that I would want to factor out a common factor. Yep. And often that's going to be useful. Only do that if I ask you to. If I just say find the derivative, do the first step and stop. Okay, I'll give you a couple minutes on 8 and 9. There's my derivative for number 8. For number 9, whenever you have a radical, always a good idea to rewrite it as a power first and then apply the power rule. The way you write the answer will depend on what you're asked for in the question. If all it said was find the derivative, the first step is good. And notice I'm using Leibniz's notation this time just so you get familiar with it. Dy dx means the derivative of y with respect to x. So it's the same as y prime. Any questions with 8 or 9? We're good? Okay. Anybody need this page still, or can I go on to the next page? Okay, why don't you try these next few questions? And we'll go over them shortly. 7 and 8, any questions with those derivatives? Yep. For number 8, I put d over dx just so you get familiar with this notation. It means the same thing. Derivative with respect to x of the g of x function. Often what we'll do is we'll just write g prime of x, because that's a little bit quicker, but I want you to get familiar with the notation, so I'm going to keep bringing it up. Sure.
So why don't you use dy over dx?
There'll be certain times when I'll require you to use it, but so far I'm not requiring it, and I'll tell you when later on. For now, I just want you to see it so you get familiar with it and you recognize what it means. Oh yeah, so in this question, because we don't have any y's, then I don't write it as dy dx because this wasn't a y equals 2 over x cubed, it was g of x. So I need to use the notation that I was already given. Yes? Yep. If we were given y equals the function, then we just write dy dx equals the derivative. Yep. Okay, so then the next two questions, what we're doing is we're finding, because remember, each of these is giving us the function of the slope of the original. And so for any x value I plug in here, it's telling me the slope of the tangent line to the original function. So for number 9, I'm just asked to plug in 2. So this is telling me for the f of x function, where x is 2, what's the slope? The slope is going to be 34. So it's really steep where x is 2. For number 10, same idea, but again, I wanted you to see the kind of notation that's used with the dy dx. So I have the d dx of the function g of x, and then we do this line, and then say, oh, my x value is equal to 1. So then I'm just plugging in 1 in place of all the x's in the question from number 8. And then we would just evaluate that, which I haven't done yet. But that'll be -6 plus a half. So -5.5. And we could write it as an improper fraction, could write it as a decimal. We're not told how to write the answer for now, so that's good enough. Yep.
When we differentiate it, like in number 8, does it matter like how simple it is? Like if the negative 4 goes into like the x over, like the x goes into the denominator?
So if I don't tell you how to simplify it, then you can just do the first line, and that's good enough. On the previous page, you'll see that for this last one, I did a couple steps. Since my original question had radicals in it, I just rewrote it so my derivative had radicals as well. So often that's what we'll do. But when we come to the test, then what I'll say is don't simplify unless I tell you to. If you simplify, that's okay, as long as you don't make a mistake. But there'll be times that I'll ask you to simplify or put it in a simplest factored form, and we'll talk about that more with tomorrow's lesson. Good? All right. So for number 11, this is saying we want to find the derivative of the function when the x is 2, which means we want to know what's the slope of the tangent line to this curve here when our x value is equal to 2. So we'll start by finding the derivative, then we'll plug the 2 in, just like we did for these previous two questions. It's just now we're being asked to do it all in one step or as part of one question, but it's still, there'll be the multiple parts. On the right-hand side, we have this product. At the moment, we don't have any way to find the derivative of a product. You can't just do the derivative of the first term, multiply it to the derivative of the second, because it doesn't give you the correct derivative. Tomorrow, we'll look at what the product rule is and prove that one too. So for now, we'd need to expand this first, then take the derivative, then plug in the 2. So I'll give you a head start on that. I'm getting 4. Did you get 4? Some of us did. Anybody have a question for me? Here in this line where I showed the minus 0 plus 0, usually we won't show that. I just wanted to remind you derivative of a constant is 0. Are we ready for number 12? So for number 12, we'll take the derivative. And then we can plug in the negative 1. Are you good with getting a slope of negative 6? Okay, so now, if I'm going to use the point slope form, I need a y-coordinate. So I haven't done that yet, so I need to come back to this original function here and say, well, what is f of negative 1 equal to? So I can find the y-coordinate. So that'll give me a 1 minus 6 plus 8. So give me 9 minus 6, which is 3. So there's the y-coordinate that goes with that x. And so my equation, y minus 3 equals my slope of negative 6 times x minus negative 1, which will be plus 1. And then I'll rearrange it to put it into general form. And there's my equation. So I'll get you started on this, and this is where we'll end off for today because we only have like 3 minutes left. And as you heard earlier, just a reminder that perpendicular means my rise and my run, they flip. Oop. Yeah, so if I want something perpendicular, well, there we go. That would be perpendicular. My rise and run switch places, and my slope switches from positive to negative. So we'll start tomorrow's class by going over this question.